Okay, so section 10.3 is dealing with hyperbolas. It's the last of our conic sections. This little video here shows how you can create a hyperbola using some special polar graph paper and using the definition. So if you remember in an ellipse, for any point on the ellipse, the distance from that point to one focus plus the distance from that point to the other focus was a constant. For hyperbolas, you can see from the formula here that it's the difference in those distances that are constant. So a point on a hyperbola, we're still going to have two foci, but the distance from that point to one focus minus the distance from that point to the other focus, the absolute value of that difference, or the distance, you can think of it as a distance, right? Difference of two things. So the difference of those distances, but the absolute value of it will be constant. And we're going to play around with that in this little PowerPoint video. So hopefully you've downloaded this this PDF that has this graph paper on it, like I'm showing you here. We actually can do the same thing that we're doing for hyperbolas for ellipses. So if you want to go back, this particular PDF that is linked with this is two pages. One you could do an ellipse on, and one we're going to concentrate today on doing a hyperbola. All right. So the difference that we're going to do, and so you couldn't do any difference you wanted necessarily with this graph paper. This graph paper has some limitations to it, but we're going to choose a difference of 6. So let's look at a little table here. And so the distance between F2. Now also look at this look at the graph paper for a second. So if you look at the focal point in red, F2. Notice I numbered all of the circles that are concentric around that have that F1 as the center. I'm calling them C1, C2, C3, C4, C5, and they go on. So that's like how many units. So C6 is 6 units away from F1. Okay. And similarly around F2. So the focal point F2, I call those circles S1, S2, S3, so to differentiate between the two circles. So S9, for example, is 9 units away from the focal point 2. Okay, so we want to look at points where the distance between that point and the focal point 2 minus the distance between the point and focal point 1 is a constant 6. So let's just start with circle S8. So all of the points on circle S8 are exactly 8 units away from the focal point 2. So our point P is going to be on that circle somewhere. And then if we look, well, we want the difference to be 6, so that means we should look at circle C2. And so the point that intersects, the intersection point of those two circles is a point which is 8 away from F2 and 2 away from F1. So the difference in those distances is 6. All right, so now let's think about where we should go next. So I'm going to make the distance between point P and F2 9. So now I know that point is definitely on that red circle, because everything on that circle is 9 units away from F2. And if I want the distance to be 6, the difference to be 6, then I guess I'm going to use circle C3. So circle C3, so that's a difference of 6, and those 2 points, right? So those points are 9 away from F2 and 3 away from F1, and so those 2 points are on our hyperbola. All right, we can continue with circle 10, S10. Well, the difference would be 6, so that means we would have to use circle C4. So circle C4, and the intersection of those 2 points will of course be on our hyperbola. We can continue this. So 11 and 11 of course would be circle 5 for the other set of circles. that difference would be 6. And we could continue. So 12 and 6, 13 and 7, 14 and 8, and then 15 and 9. All right, now pause this video and try to do the other half of this. I think you have one full table on yours, but we could sort of reverse these, right? We could start with 2 and 8. Now that difference is going to be -6, but we're looking for the absolute value of it, so that point will be on the same hyperbola. 3 and 9, 4 and 10, 5 and 11, 6 and 12, 7 and 13. So the exact same numbers we did before, but now we're in reverse. So the difference in these numbers would surely be -6, but again, we are not concerned with the negative because we're taking the absolute value of the difference. All right, so all those points, if we connect them, that's going to be the hyperbola. Hyperbola, of course, is continuous, so we would just connect that with a line, with a curve. So notice too that as you get further and further away from the foci, this curve tends to look more and more linear. And there's a reason for that. These things are asymptotic. So these endpoints, the ends of these, they go on forever without end, but the curves as they go out get more and more linear because they get closer and closer without touching these asymptotes. Now we've dealt with asymptotes before. The asymptotes we dealt with for the most part were perpendicular. We had vertical and horizontal asymptotes. These are slanted or skewed asymptotes. And those asymptotes will be part of the guides that we will use to actually sketch in. We will not, when we go to create and draw our asymptote, our hyperbolas, we will not generate all these points. This was just to kind of play around with what the definition is telling us. All right, so we just looked at a video on how to create a hyperbola using some circular graph paper, and by using the definition of what a hyperbola is, based on the fact that it's a set of points. Actually, I guess this should have absolute values around it. It's the set of points P such that the distance from P to one focus minus the distance from P to the other focus is always a constant, or the absolute value of that distance, I guess, technically speaking, would be a constant. As it turns out, that constant is 2a. It's 2a for hyperbolas, as well as the definition for ellipses was also 2a. In that case, we were adding the differences, the distances between the point and the two foci, but here it's the difference, actually the absolute value of the difference of those distances. All right, so let's look at some terminology. I have on your notes sort of a hyperbola already sketched for you. And so let's look. So the vertices, we have vertices again. Ellipses, we don't typically think about it having vertices. Our textbook does use the endpoints of the major axis to be vertices. I don't tend to refer to those as vertices, but some people do. In this case, just like a parabola has its vertex at this lowest point, or here the most right point, and this to the most left point. So same thing's going to happen with hyperbolas. So those are the two vertices. The distance from the center, which I'm calling HK, and we'll use that same nomenclature here. The distance from the center out to the vertex is referred to as A. And then the distance from the center out to a focus, that's going to be C. So you can see in this case for hyperbolas, C is going to be bigger than A. All right, so if we draw an axis through the vertices, we refer to this as the transverse axis. Now, this axis, you can think about continuing it, and it contains the foci as well. And refer to this as the transverse axis, and it's the axis that gets traversed or crossed by the hyperbola. Now, often when we say the endpoints of the transverse axis, we think about the vertices. So we sometimes will, if it's convenient, we'll think about the transverse axis length as being 2a. Sometimes we'll think of the transverse axis as being a line. Sometimes we'll think of it as being a segment and its length being 2a. All right. So the other axis, which kind of goes through this way, which will be associated with B. So if we go out from the center B, well, there's nothing really there. We don't call this point anything special, as far as I'm aware. But it's the dimensions of the box. This B helps us create the dimensions of the box. So in this case, the height of this box is 2b. We will often refer to this axis, on which nothing really lies except maybe the center, I guess, if you want to think of it that way, as the conjugate axis. Okay, so the conjugate axis is the axis which we run along plus or minus b from the center, and the transverse axis is what we run along the a. So in the other conic sections, we sometimes think of drawing a little right triangle, so we can do the same thing here. So if we draw a right triangle from the center out to the corner of this box, we know this side is A, this side is B. Well, I don't know if you can really tell, but if I swing that down, if I took that segment from the center and swung it down, it would hit the focus point. And so that distance will be the C. It's not a coincidence, it is equal to our C. So we're going back, the whole point of all this is that we're going back to B squared plus A squared is equal to C squared. So it's clear that C is the bigger one here. It's certainly bigger than A. But if we look at it as the hypotenuse in like this right triangle in here, then we can see that C is the biggest of all three of these, A, B, and C. Note too that in an ellipse, A was always the biggest of all three, so it was certainly bigger than B. But A does not have to be the bigger of the two, A and B now. It can be, but it doesn't have to be. All right. So so this is, and then what we'll do is we will draw through. The whole point of making this box is it's an aid in helping us sketch our hyperbola. So if we draw lines going through each corner, the center and the opposite corner, and we do that same thing here. I actually already drew part of it as my right triangle, and I do it here, then I'm creating two asymptotes, and those are the asymptotes that these hyperbola curves are going to get closer and closer to, but never touch. And so that's the whole point of creating this box. And when we graph a hyperbola, we're going to go from the center, we're going to go over left and right A. If this is the transverse axis is horizontal, we're going to see cases where the transverse axis could be vertical like this. But in this case, we go left and right A, and those give us our vertices. Then we go left and right C, that gives us our focus, our foci. And then we go up and down, again in this case, up and down B, and then through the vertices and through these points out here, up B and down B, we create a rectangle, and then we draw our asymptotes in there. So then what we do is we just say, okay, well, I know my vertex is, and we just kind of sketch it in. For parabolas, we would do about 5 points on the parabola. Here, we're not going to try to create other points. You can see these would all be pretty nasty points to try to graph. So we don't use a table or anything else. What we do is we just kind of sketch it in. We try not to cross, touch, or curve away from the asymptotes. They would get closer and closer, never touching. And then they go on. You know, I didn't put arrows on mine, but you could. Those go on forever and ever. Okay. I'm hoping that on your PDF you have the ability to click on this Desmos, this Desmos link. So if you click on that while you have your PDF open, see if it works for you. For me, it opens it up in Desmos, and it's a file that I've created that has a sideways hyperbola, and the resulting box created by A away from the center goes to the vertex on either side, and then in this one up and down, B away from the center. And if we create that box, then that box is what the corners through which are our asymptotes, which sort of defines our hyperbola. So what I have on this is I have a couple sliders. And so H, for example, if I move H, that's changing the X coordinate of my center. And then I can adjust K. Now I made these integer values. The center doesn't have to be right at integer values, but just to keep this a little bit simpler, I made my H and K integers. And then I also have a slider for A, so I can change how big or how small A is. Here, A are intervals of half, so that, you know, again, A can be any value, but here I just kept it simple. A is either integers or halves. And then B, I did make B a continuum, so I can make B as big or small as I want. So you notice that when B is smaller than A, the hyperbolas tend to be very narrow. But when B is bigger than A, they tend to be very wide parabolas. Okay. And then also, if you look at the top of this file, you can see all these things marked in red. You know, you can turn each one of these things on or off by clicking on the little circle, and that turns on or off the hyperbola. And so what I have all these that are for this hyperbola. Let me click them all so they all turn off. And then if you go below the sliders, I have a whole other set of graphs, and those are for a hyperbola that opens up, that has a transverse axis that is vertical. So again, those also work with the same H, K, A, and B for that parabola, that hyperbola as well. So feel free to play around with that and get a feel for what things look like. I hope you can open it. I was able to through on my PDF. I hope you can too. All right, so let's talk about an example of a use of a hyperbola and how in science we might see the use of a hyperbola. So when they actually discovered hypersonic, supersonic flight, that means airplanes that would go faster than the speed of sound, or larger than Mach 1, faster than Mach 1, the plane ends up creating a shock wave. And it ends up being a cone that's created by the leading tip of the plane. And then what happens is, so this is a cone of energy, and it interferes with the Earth, you know, basically assuming the Earth is flat, and it's not a bad approximation, assuming you're looking at just a small portion of the planet. So you think of it as a plane. And then the intersection of that plane with that cone, as we saw the other day when we first started talking about conic sections, that intersection would be a curve, which is a hyperbola. So interestingly enough, the first time they did this, they didn't know this was going to happen. And they ended up doing damage to all the buildings on the military base that the plane was flying over. Probably was flying too close and was too low, and the energy didn't have a chance to disperse as much, and so it damaged a lot of the buildings. I imagine it blew out windows. So they don't tend to fly hypersonically over ground area where people live anymore because it creates a very loud boom in the sky. You hear it, but you just don't know where it's coming from or why. So they tend to not go supersonic until they're away from populated areas. All right, and then this is an interesting photo I found online where you can kind of see the cone coming out of the back, the middle of the plane, due to the humidity at the time that the photo was taken. You could sort of see the actual sonic cone formed, by the plane. All right, so let's look at, we talked about up here the different components of a hyperbola. This one has transverse axis is vertical, as horizontal, sorry, and that's kind of similar to this one. We've got all the components drawn in. Remember that C is the biggest here. A in this one is the bigger of the two, A and B, but it doesn't have to be. I kept these values really simple. A is 4, B is 3. We know, of course, in a right triangle with those two edges, that this length here would be 5. That is not a coincidence that that's the same. If we were to rotate that edge down, it would be right here. C is 5 in this case, so I kept it pretty simple. These are examples, too, of equations where the center of the hyperbola is at 0, 0. So you don't have the x minus h and the y minus k like you would on the next page when when the center is no longer at 0. But let's just start with the simplest case here. The biggest difference you see is that there's a minus between. In the ellipses, that was a plus sign. Here it is a minus sign. Now again, A and B are not necessarily, A is not the biggest, but what we do here, if you notice, look down here, the A squared and the B squared stay where they are. What happens is the y squared and the x squared change. So when the x squared is negative, we put it second. So you can think about the A switching to be under the y, but because the x is negative, we no longer keep it out in front, we'll switch them. So it looks like the A and B didn't move, but the x and y did. In reality, the A is under the x. Here, the A is under the y. We just, like when we write equations, we'd rather not have the negative out in front, and so we swap the x and y. Okay, the foci are located from the center plus or minus C. Here, we're adding this plus and minus C to the y coordinate, in this case is 0, but so it's a 0 minus C to go down to focus, and 0 comma positive C to go up to the focus. So that's the focus here, and this is the focus here. Notice in this case, A is not the bigger of the two. Again, it doesn't have to be. It's A, the general formula, A squared plus B squared is equal to C squared. Clearly, the C is the biggest in this case. It's the distance from the center out to a focus. All right, we will in some cases be interested in the equation of an asymptote or the slope of the asymptote. So the slope of the asymptote is always going to be either A over B or B over A. Remember, if we think about starting at the center, we talk about rise over run. So in this case, it's B over A. In this case, A is up, so it's rise over run. It's going to be A over B. So it just depends on how the orientation is. Here the equations are pretty simple because there is no y-intercept. The y-intercept is 0. You should be able to write the equation of the line, but we're going to often think about, well, what's the slope? And of course, it's a positive, but also it's a negative slope as well because there are two asymptotes, so it's plus or minus. All right, moving on to page 2 of our notes for hyperbolas. Example 1. Now again, these are centered at the origin. In this case, it's pretty easy to see because the foci are at 6, 0 and negative 6, 0. Midway between the two foci is the center, so we could pretty clearly see that the center, even if we didn't know that all we're dealing with so far is hyperbolas with centers at 0, we know that the midway between the segment with these as endpoints would be 0, 0. All right, that also allows us to see that C, the distance from the center to one of the foci, is C, and so that distance in this case is clearly 6. All right, and then also they say the distance between the vertices, and they give us a hint, that's 2a, is 8. So A is clearly 4 in this case. So we can use C and A to find our B. Well, let's back up for a second. We're trying to write the equation of the hyperbola. What do we need in order to write the equation? We need the location of the center, the H and the K, and we need A squared, and we need B squared, and then finally we need to know the orientation. So if we look at these two points, these foci, they're on the transverse axis. Are they next to each other or above each other? So that tells us these are clearly next to each other. So that means the transverse axis is horizontal. So we know the orientation, we know the center, we know A, so we know A squared. We need to find B. So we know that C squared, 36, minus A squared, which is 16, will give us B squared. And so B squared is 20. B squared is 20. So I could find B, but ultimately when I write my equation, I need B squared. So I'm not going to bother trying to simplify that and figure out what your B is. And so our formula is going to look like this. In this case, it's horizontal, so I know my x is here. I'm going to write x minus 0. You could just say x squared. And then this is going to be y minus 0, or again, could just be y squared. But this is sort of a more generalized formula. And then always here in hyperbolas, this is always our a squared, so this will be 16. And b squared is 20. So in this case, our a is clearly smaller than our b, and it's horizontal. So this is the equation of that hyperbola. All right, example number 2. Again, we don't have any x terms or y terms, so it's pretty clear this is also centered, again, at the origin. What we want to do is divide through by 400 to make that a 1. We divide each of these by 400. Also, you can see the x squared term is negative, so we'll write that second. We'll put the positive one out in front. So this ends up being y. This time I'm just going to say y squared. I could say y minus 0, quantity squared if I wanted, over 16 minus x squared over 25 equals 1. All right, so to graph this thing, I need to know where the center is. Clearly, the center is going to be at the origin, so I can just plot the xy axis right in the middle in this case. I don't know, something like that, I guess. So that's my xy axis. In order to graph this thing, and I'm going to include the foci. So I know my A is 4, my B is 5, my C squared is the sum of these two, so that's 41. So C equals the square root of 41. That doesn't really simplify, but we could get a decimal approximation because, you know, square root of 41, I don't know how far that is, right? So, but we think about that, that's approximately 6.4. So when we plot our foci, that'll come in handy. All right, if we're asked to say with the exact value, probably be better to go ahead and leave it as the square root. Okay, so with this, orientation is vertical because the y is first here. So I'm going to go from my center, I'm going to go up A, 1, 2, 3, 4. So there is my vertex. And then while we're at it, 5, 6.4. So there is my focus. Going down, 1, 2, 3, 4. That's my vertex. by 6.4, something like that will be my focus. All right, then we look at our A and we go over 5. Our B and we go over 5. 1, 2, 3, 4, 5. And 1, 2, 3, 4, 5. There's nothing really there, but we're going to use that to create our box. And then we're going to sketch or dash in some asymptotes through the corner, through the center, and through the opposite corner. And so these are my vertices, here and here. And so now I just sketch it in. This one's fairly wide. Again, use the asymptotes as guides. That one was a little flat, but you know, it's going to have to be a pretty poor graph for me to take off any point. So something like that. All right, so both of these examples had centers at 0. Now let's talk about what happens if the center is not at 0. So as you probably guessed, it's x minus h and y minus k. If they flip, because the y is first, just be careful, the k stays with the y, the h stays with the x. We saw a similar thing in sideways parabolas when the x was in the parentheses next to the y, the h was in the parentheses next to the x. Same thing sort of happens here. All right, so from the center, which is no longer at the origin, but at hk, to get my foci, if it's horizontal, I'm going to add and subtract c from the h coordinate. So h minus c, comma k, and h plus c, comma k will be when the transverse axis is horizontal. When it's vertical, I'm going to add and subtract c from the k coordinate, the y coordinate of the center. So the foci are going to be at h, comma k minus c, and h, comma k plus c to get our two foci out here. The slope of the asymptote, similar to what we had before. So the slope of this is going to be b over a, but there's a positive and a negative, so we do plus or minus b over a plus or minus a over b. Okay, depending again whether it's vertical or horizontal. The slope of that line is going to be a rise of a and a run of b, and then negative a, positive b to get the other one. All right, so let's look at an example here, number 3. Graph this. So first, in order to graph this, we really want to put this into one of these two forms. We can see that the y is negative, therefore we know that the orientation is going to be what? The transverse axis will be horizontal in this case. Okay, so when we want to complete the square, we got to complete the square for the x and for the y, very similar to what we did for ellipses. We will also factor out these coefficients at the same time. So we do. And I didn't leave you a whole lot of space, so I'll write kind of small here. 9 taken out of the x squared. We also take the 9 out of the x term, so plus 2x, and I'm going to leave a space for what we put in there to complete the square. And then we take a negative 4 out of the y squared. We also take it out of the negative 24y. So be careful, this is plus 6y. Leave a space. We'll move the 63 to the other side. All right, I'm going to add half of this squared, which is 1. Now what's the true value of that 1? True value of that 1 is 9. So we are going to add 9 to both sides. Okay. What are we going to add here? We do half of this squared, which is 9. So think about what we're going to add to the other side. That was really a trick question. We are going to subtract. That 9's true value is negative 36, so we subtract 36. Okay? And so let's write these as perfect, as binomials squared now. So we have 9 times the quantity x plus 1, quantity squared, minus 4 times the quantity of y plus 3 squared equals, and we combine all that, we get 36. Okay? If this were negative, it's not a big problem. We would simply multiply through by a -1, and actually the sign of these things would change. So it kind of looks like x is positive, but in reality it would flip and the y would be positive and we would put it first. So it does change it. If for some reason this ends up being negative, for an ellipse that would cause us a problem. But here, if this is negative, it's not a problem. We divide through by -36. It will flip the signs of these, so it would make it, change from being horizontal to vertical. So we really, I guess maybe we shouldn't really have tried to determine that quite yet. We got lucky in this case because the y was negative, but in reality, when if this had been positive, when it moved over, it would have been negative, and so this would probably be a negative value. So just be careful. I guess I shouldn't have asked you at the beginning. We got kind of lucky. This could be negative here, and in which case, instead of being horizontal, it would be vertical. So be careful with that. All right, and so finally, the final form, we're going to divide through by positive 36 in this case. So x plus 1 quantity squared over 4 minus y plus 3 quantity squared over 9 equals 1. All right, so let's write down. We're asked to find a bunch of stuff here. So how is the orientation? We know the orientation is horizontal, and you're still right there. Let's find the center. The center is -1, -3. And so we can think about that being in the center here. We don't really need to plot that point. It's not really part of the graph, but if we put it here, then if that's going to be -1 in the x direction, I need my y-axis over here. And if it's -3 down, I'm going to go up 3, 1, 2, 3. That will be my x-axis. It's always nice to put the center right in your middle of your graph. If I just put my xy axis right in the middle like we did for the previous one up above, we probably we might not be able to fit the hyperbola in there. Okay. So let's find the vertices next. And so this one's horizontal, so I go A over. So this is always our A. So in this case, A equals 4, A equals 2, B equals 3. So I'm going to go, here is my vertex, 2 over from the center, 2 over from my center. So that's my vertex and my vertex. And then I go down 3 from the center, 1, 2, 3, and I start drawing my box. I go up 3. This one's going to be right on the x-axis. It's going to be a little harder to see. Okay, and through those I draw asymptotes. Sketch them if you will. Something like okay. And then we could just sketch those in. Now, sometimes it's going to be vertical. The transverse axis is vertical. In this case, the transverse axis was horizontal. So sketch that in as well. Sometimes it's nice to do your graph before you find the vertex, because now you can see kind of clearly where the vertices are. If you want to just start with the center and say -1 plus or -2, -3, that's fine. You don't have to list both of them. You could write it like that. I'll be okay with that. All right, and so the foci, we need to find what C is. So the foci, using A and B, we can find C. So C squared equals the sum of these two numbers, which is 13. So that means C is equal to the square root of 13, which is approximately 3.6. So we can then plot those. So that was 2 away, 3.6. There's my focus. That was 2, 3.6. So there's my other focus. Okay. Let's put the exact values, though. We would say, similar to what we did with the vertex, we have -1 plus or minus the square root of 13, comma, -3. So we go square root of 13 this way, square root of 13 that way if we want an exact value. And then finally, if we look at what the slope is, we're going to go up b and over a. So this is plus or minus b over a. So there's our slope, plus or minus, because remember there's 2 of those. And now domain, one other thing that we were asked to find. So, I would say look for the domain after you've graphed it. It's a little bit easier. The domain here is going to be, well, any value back over this way, because these things are going to be going forever in those directions. So that's starts down at -infinity up to and including, looks like what, -3. And then starting at +1. Inclusive of +1 out to infinity. Hopefully you wrote small. I didn't give you a whole lot of space here. That's the domain, and then the range is the possible y values. Well, the y values, these go on forever. There's no limitation to what y values it could take on. So we'll say -infinity up to infinity. All right. Example 4 then. Write the equation of this hyperbola. So in order to write the equation, we need a number of things. We need h, we need k, or the center, we need a squared, we need b squared, and we need to know the orientation. How it's oriented. All right, so we can look here. We know the vertices is here, the vertex is there. And so we can tell from that that A is going to be 2. And they were nice and they drew our box for us. And so that box tells us that B is equal to 3. We don't really have to find the C in this case, but the center, that's pretty easy. It's where the asymptotes intersect. So I think if you look at that closely, you can see that the center for h and k is going to be 4, -5. The orientation, or the transverse axis, is vertical. And so we know everything we need. We didn't write down a squared and b squared, but we know what a and b are, so we can write that. And the vertical orientation tells us that we're putting our y first. So it's y plus 5. Remember to put your k next to your y. And a squared always goes here, so that's 4 minus x minus 4 quantity squared over, and then this is b squared, or 9, equals 1. Okay? All right, so the last 2 examples are dealing with or using this idea of eccentricity. Now, we talked about eccentricity for ellipses. And for that, it was between 0 and 1. Remember, 0 is this perfect circle. 1 would be sort of a flat circle, or a line almost. We sometimes think of it as parabola, technically speaking. And so C, in this case, C is bigger. It's still C over A, but C is bigger than A in this case. And so for a hyperbola, the eccentricity will always be greater than 1. All right, but it is still C over A, like we saw for an ellipse. So in this case, we just need to find C over A. So we found, we can find A, that's easy enough, that's 3, because this is A squared. And then C squared is the sum of these 2 things, so C squared is 25, so C is clearly 5. So E, the eccentricity, is 5/3. All right, last example. They're giving us the location of the vertices and the eccentricity. They want us to write the equation. So again, we need to know h, we need to know k, we need to know a squared, we need to know b squared, and we need to know how this thing is oriented. All right, so if we think about the vertices, what's midway between the vertices? The center. So from these 2 point locations, we should be able to find the center. And so the center is going to be -2, comma, and then we add these, the y coordinates we add up and divide by 2, so that will give us 1. So the midpoint of a segment that has these 2 points as their endpoints, the midpoint would be -2, comma 1, so that's my center. So I found my h and I found my k. Now, also, the distance between these 2 points, that's equal to 2a. So the distance between those 2 things is 8. So that gives us an a value of 4. All right, so we know our a. We just need to find our b. And also the orientation. So these vertices, are they next to each other or above each other? They have the same x, so of course these are above each other. So the orientation is vertical because the vertices are on the transverse axis. Okay, so we simply got to find that c over a, we know that's equal to e, so we know c over a is 4 is equal to the eccentricity, which is 3, so that means c is equal to 12. So now let's try c squared minus a squared equals b squared, and so that is 144 minus 16 is equal to b squared, that's 128. And so we're not interested in trying to figure out what b is. We don't really care what b is. We need b squared in our equation. All right, and so this is vertical, so I'm going to start with, let me get this vertical sort of out of my way so I have a little more room. So I'm going to start with my y since it's vertical, so y minus 1. Be careful, it's not the 2, it's the 1 we're using. So y minus 1 quantity squared over something, and then let's go back and say x plus 2 quantity squared, so that gives me my center, over something equals 1, and so now we just got to figure out, so this is our a squared, remember that our a is 4, so this will be 16, and then this is b squared, 128. Okay, so that is our equation. All right, so you have your homework, and it's listed here.